So next example and our final example, hopefully this is all making sense. It's a little bit of a complex problem, but I think you guys can crank this out, okay? So example 3, okay? So person pulling. Okay, I'm gonna have to write this out, so bear with me for a second. Pulling box with force of 100 newtons, okay? Period. Before period, for 10 meters, okay? Box weighs 5 kilograms and coefficient, oh my goodness, coefficient, spelling, come on, bear with me. Coefficient, if I didn't spell this correctly, don't make fun of me, okay? Coefficient of kinetic friction. Instead of writing all this out, let me just make it straightforward. And mu k equals 0.2. Okay? What is total work? Let's do this, okay? So, since I tell you the coefficient of kinetic friction, okay, that's what mu k represents, and I made this number up. I didn't look this up in a book for the material I'm dealing with. I just made it up, okay? So bear with me. So since we know since I'm talking about coefficient of kinetic friction, it's fair to assume that we have kinetic friction present in this case. So what I would do, this technique, like as you have seen in every single problem so far, that I've drawn a diagram, and it's really helpful to do that, okay? The basis of doing work problems are forces, so draw those force diagrams. So let's do that, okay? So you want to find what is the total work. So in order to find the total work, you need to find the work done by each and every force present on the box. So that's why those force diagrams are really helpful. So what I would do is I would draw my box. We know it's 5 kilograms, so let's draw our forces first. So we have a force of pull, pulling to the right, okay? I'll make it clear, pulling to right. Because I know some people in the comment will be like, you didn't designate which side we're going to. Nonetheless, okay? For those people that are mellow, I appreciate it, but those who are tight about everything, relax for a second, okay? So I'm just giving you guys a hard time, but I gotta add some levity to the situation, right? So force of pull is to the right. There's gravity obviously present, right? So if anything has a mass, there's going to be some type of gravity that's being performed or done or put onto that object, okay? So for example, in this case, the force of gravity is it's the weight, which represents mg. First, let me write what the force of pull is. It's 100 newtons. The force of gravity, which is the weight, which is mg, equals the mass, which is 5 kilograms, times the gravity. I'm going to approximate to 10 meters per second squared, and that equals 50 newtons, okay? See how I did that? Force of normal is the force perpendicular to what the object is resting on. So it's going to be perpendicular to the ground, okay? So if it was on a table, it'll be perpendicular to the table. If it was hanging, for example, if the object was on a wall, this is our wall, the force of normal would be perpendicular to that wall, and that's where the force of normal would be. So that's what the force of normal is. So that's the force of normal. The force of normal in this case, so since the box is not, I did not say or state in my question or in this example that the box is moving in the y direction. So it's fair to assume that the forces in the y direction cancel one another out. So it does not move in that y direction. So in this case, since the force of gravity is 50 newtons going in the down direction, the force of normal has to also be 50 newtons going in the opposite direction, which is the up direction, since it's not moving in this case, since I did not specify that the object is not moving in the y direction, okay? Now if I were to say the object is moving in the y direction, then it will make the problem more complicated, but nonetheless, since I'm saying the box is sliding on the ground, the box is being pulled on the ground, is being pulled to the right, it's fair to assume that there's no movement done in the y direction, so the forces in the y direction have to be equal and opposite of one another. But in this case, I just specifically wrote the magnitude. That is, I didn't worry about the signs yet until we plug it into the formula. Okay, so don't worry. But essentially, these have to cancel each other out. They have to be of equal magnitude. Okay, so enough about that. So the final force we need to talk about is the friction. Since it's being pulled in this direction to the right, the friction force has to be in the opposite direction. So the force of friction has to be to the left. So I'll put force of friction. Now the force of friction in this case is about equal to mu k times the force of normal. So in this case, mu k is 0.2 times that 50 newtons. So it'll equal 10 newtons, okay? So there you have it so far. So we identified each and every one of these forces, their magnitudes, their values, okay? So now once you do that, it makes the problem straightforward. Now in order to find the total work, you want to find the work done by each and every one of these forces. Once you do that, you sum them all up together and find your total work. It's as easy as that. Let's not make it complicated, okay? So I'm going to erase all this little busy work I did. I'm just going to write the values that I found for each and every one of these guys, okay? So I have some space to work with. So force of gravity we know is 50 newtons. We'll worry about the signs later on, okay? The negatives and the positive. Force of friction we figured out was 10 newtons, okay? I'll put it right here, 10 newtons, okay? So now let's find the work done by each and every one of these guys, okay? So the work done by the force of pull. So work by pull is equal to the force cosine theta times the displacement, right? So the work done by the pull is equal to the force, which is 100, cosine theta. I'm gonna write the units so I have some space, so bear with me. Cosine theta times the distance that is traveling is 10 meters. Okay. Now the angle is very important. In this case, since the box is moving this way, 10 meters, okay, it's fair to assume that since the box is being pulled to the right, that it's moving to the right. So the force being applied on the box is in the same direction of which the box is moving. So that angle is going to be 0. So work done by pull is going to be, this is going to be 1. The cosine 0 is 1. So 100 times 10 is going to be 1,000. So work done by the pulling is 1,000 Newton meter. Okay, that should make sense. Let's tackle force of gravity. Okay, force of gravity will be work done by gravity, which equals force cosine theta times distance. Force is 50 cosine theta, we'll talk about that, and times 10 meters. Okay, now we could address this from two different perspectives. We could do it from the angle. Now, in order to determine the angle, we could look at it from two different perspectives. It could be 270 or it could be 90. Doesn't matter which one you pick. Cosine of 270 or 90 is going to be 0. So essentially, we'll pick 270 for example. So essentially, this is going to be 0 newtons per meter. The work done by gravity. Okay, and that's a really important point, because as you've noticed, the force of gravity and the force normal is perpendicular to the object's movement, right? So that's why when I wrote the formula the first time, I wrote parallel. The forces that are parallel to the movement of the object, there's going to be work done on it. In the cases of forces that are perpendicular to the movement of the object, the work is always going to be 0, as you see in this case. So in this case, the work done by the force of normal, since it's perpendicular to the movement of the box, is going to also be 0. So work done by the force normal is also equal to 0. And finally, force of friction is parallel. It's on the same direction as the movement of the box. So there's going to be a value for the force of friction, for the work done by the force of friction. So we have to calculate that out. In the case of gravity and normal, since they're perpendicular, since they bisect the they're perpendicular, they bisect the movement of the object. Since it's perpendicular, is going to be 0. These ones are parallel. There's going to be a value for these forces, okay, and for the work. Okay, so the work done by the force of friction, okay, is going to be F cosine theta times D, right? F is going to be 10 cosine Let's see, cosine 180 is going to be -1, I believe, times it by distance, which is 10. So 10 times -1 times 10 equals -100 Newton meter. Okay? Pretty straightforward. So this is 180 degrees if you guys want to see that clearly. Okay? So 10 cosine 180 times 10, so 10 times -1 times 10. This is cosine 180 is -1, that's where I got that from. The value you get is -100 newtons per meter. But in this case, I'm focusing on the magnitude. I'm not worried about the signs, we'll worry about that later. It's 100 newtons per meter, okay? So we found all our works, okay? Now all we have to do is add them all up together. But now the signs are extremely important to keep track of, okay? So the way I'm going to designate my x and y axes is a very standard way. X is going to the right, which is positive. Positive x is to the right. Positive y is going straight up, okay? That's the way we typically see an x and y coordinate. So now, in this little small region right here, I'm going to figure out the total work, okay? So, since the force of pull, this is the way I've designated my x and y coordinate, since the force of pull is being pulled in the positive x direction, it will remain as a positive. So total work, total W is equal to this is the force, this is the thing I'm talking about, 1,000 plus, let's worry about the other one, work done by friction. Since if right is going positive, so this work that's being done by the force of friction, which is pointing to the left, this is going to be negative, and we calculated that out, so that's going to be a negative, so minus 100. These guys are 0, so we don't worry about that, but I'll just put it plus 0, plus 0. And the answer we get, this little small corner, is 900 Newton meter. And there you have it. We're done with this problem. Tough problem, slightly, not too bad. Let me know what you guys think. This is how you do work problems. There might be some problems which are much more complex than this, but this is the basics that you guys should be familiar with. When you got the basics down, then the more complex problems become much more easier. So I hope this helps out. I hope this all makes sense. You know, I wish you guys the best, okay? So, like this page, tell your friends and family about it. This is MoBaller12 signing out. Bye-bye.